homework stuff? Anything? No?
No, chapter 48.
Okay. Just kind of do a really quick example of what we did last time. And then we'll do the last section in chapter 4, which is going to be nifty on its own. Somehow it's going to relate to how airlines figure out how many seats to oversell. Anybody ever been bumped? Yeah. Anybody ever voluntarily take like, we'll give you $500. Dear God, just somebody give me your seat. No? You know, has anybody ever been to an airport getting on a plane? And they say over the announcement, we'll give a free flight or $300 or whatever if you give up your seat. Well, and then a little bit later, we'll give you $400 or something if you give up your seat. No? Have you ever?
Just waiting for the number to hit their grocery list or whatever the number they're looking for on the other like, oh,
Yeah. Why does an airline overbook its flights?
People don't show up.
There's a probability that a person, every person, won't show. And what's the worst thing for an airline to do? Fly a plane with a lot of empty seats. So it's better for them to have a PR problem with a few people being bumped than it is for them to fly with empty seats. So what we'll do after this little review is we'll talk about how to deal with those probabilities. How many seats do you sell so that you don't piss off too many people, but you still make good money? So here's the review of what we did last time. Let's make up some data. I like it. So I would give you this information. Let me see what's that. Oh, that's Nina. Okay. That works out. Of course, what am I being careful about? These have to happen to be 1, which is also known as 100%. So that means you didn't lose anybody. If you calculated these and you rounded it all, that might not be exactly 1. Or if somebody gives it to you, they round it, it might not be exactly 1, but it's got to be 0.999 or 1.0001 or something. Here's the formulas we developed. The mean. Here's something really, really cool. Another name for the mean is the expected value. It's what you expect to happen, right? And what is so awesome about that word is, what's the first 3 letters of the formula? Yeah, it's expected. That's kind of nice. Ooh, yeah, ooh. It's not David Blaine, though. And the standard deviation, we kind of adjusted things a bit, both for the mean and the standard deviation, so they work really well with this format. Right? So the standard deviation was the square root. And we developed those formulas last time. Now those formulas are going to live on your formula sheet. Right? If I were you, I'd be making a formula sheet as we're doing stuff and then have it sitting next to you as you do your homework. That would be right, be smart. So even if you missed the whole discussion about where that formula came from, how do you tell what you need to be able to do this formula? Cover up the sum piece and see what column you need to create. Right? I need a column of these things, so that I can add them up. So, what do I have? And of course, what do I need for the mean? I need a column of x times p of x's so that I can add them up. So what's my next column going to be? Am I crazy? Here, go ahead and fill that in. Let me see, where's my guys? I hate it when people are good and put the stuff away. Is that you? I'm going to show you how to do this in the calculator. Yeah. Okay, let's see. So if I go to stat, edit, clear those out. Alright, so now I'm going to put in here 4, 8, 9, 11, and over here, 0.11, 0.2 at 0.51, 0.1. What do I want this column to be?
L1 times L2.
Yeah, x times p of x, so L1 times L2. So go up to L3. See that you want it to say L3 equals. L3 is L1 times L2. Pop. So there's those. Ooh. And if I add those up, what does that represent? Yeah, it's the sum of x p of x, which is also known as the mean. Why? So if I add those up, I get. So let's say one more time. 8.37. 8.37. Ooh, I like you. Does that make sense? What's the heaviest weighted thing in here? The 9. Right? And then 8's the second heaviest weighted, so it makes sense that it's between 8 and 9, and kind of, and these kind of pull it equally in both directions, right? So it kind of makes sense it's sort of in the middle. If that was the heaviest weighted thing, the mean should have been closer to 11. How we doing? Because what does this really represent? If I had 100 data points, how many of them would be 4? 11. Yeah, because that's 11 out of 1. I could have 1,000 data points, and 110 of them would be 4. It's just whatever makes 11%. Okay. Aw. So that's the mean. So I know the mean is 8.37. What's the next column going to look like? Yeah, it's going to be this piece. Because I need to add those up, so I need to make an x squared p of x column. Okay. So what I want L4 to be. Okay, cool, I like it. So I did L1 times L3, but if you do L1 squared, that's x squared.
Times L2.
Times L2, you get those, right? But if I do L1 times L3, you get the same numbers. I mean, it doesn't matter. Whatever makes x squared p of x. Don't just square these. If you square these, do I get x squared p of x? No, I get x squared p squared. I don't want that. So yes, you could square this column times this. That's x squared p of x. Or you could do this times this. That's x squared p of x. Either way. So of course the math is going to go, yeah, the same thing. Okay, I like it. And why do we need that? Well, look at the video from the other day. I'm not going to reteach that. We already went over that. So what do I put in here for the formula? So when I do this, I get the sum of x squared p of x. So what I get when I add those up, remember what's the quick way to do that? go to second stat, to go to list, math, sum. I want sum of L4 this time. Is that what you guys get? 73.09. That's the sum of these guys. Okay. Yes? So just remind you guys, so here's the one I want to sum up right now. If you get out of there, hit second quit to get out of your table, go to second stat to get to list. I want to do something with my lists. Get second stat to get to list. I want to do some math to my lists. I want to sum up which list? Second 4 to get L4. Or you just add them. Blah, 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 blah. Either way you do it. Like it. Let me see if you guys can handle this. If I do one variable stats, if I do stat calc one bar stats on L4, it gives me a lot of shit. But what's the only thing I want? That one. So if I do it on L4, this is the sum of things in L4. Isn't that what we just got? So it's actually less keystrokes if you want to do that. You just got to realize none of these other numbers mean anything. You just want the sum. All right. Why do I just want the sum? Because that's what goes into this formula. So how do I rewrite this formula now? Square root 73.09 minus 8.37 squared. That's the most forgotten little dude. Or little square. So I put in here square root. Where'd it go? 73.09 minus 8.37 squared. So I think one thing that's interesting as a math teacher, as a math person, I know that I think part of the problem students have sometimes is get very lost in all the number details. We did a lot of work together to create this formula. And the formula was built on ideas. So once I get the formula created, it does just become messing with numbers because the formula has the idea in it. So sometimes you guys become disconnected. You're like, all right, I got a bunch of numbers in this shit. But we did a lot of work to make this thing. So that part should be like just blam, 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 get numbers. So how do I write this? What's the standard deviation? Two. Okay. Or you can even put 1.7416. You have to go at least 3 places for standard deviation. 4 places, hey, that's even better. 9 places, what the hell? Stop. That's crazy. So on average, these data points get 1.7 something away from their mean. And these aren't very widespread. In fact, there's a huge chunk that are all 9s. So it makes sense that the standard deviation is relatively small. Maybe. That's section 4.1 and 4.2. Okay. If you weren't here, you might want to come up and see me after class and get a little handout that I gave out that we worked on last time. All right, any questions on that stuff there? Okay, so I don't know if you remember I told you, we're going to learn different ways for them to give us data. We're going to develop a way to get the mean and standard deviation each time. There's got to be a quicker way. I don't want to write 11 4s and 28 8s and 51 9s and make a giant table and do the x minus x bar. I don't want to do all that shit. There's got to be a quicker way given this format. There's the quicker way, those 2 formulas.
To make sure that L4, we can get it by multiplying x and L3.
Yeah, L1 and L3. I love it. I did it both ways here. I don't know if you noticed. And the numbers just stayed the same because I didn't care. Okay, I like it. So, what happened? Oh, shit, thank you. That'd be awesome.
go.
Okay. So we're now going to get into developing the math we need to be able to do that airplane problem. If you're an airplane, you owned an airline. You're like, okay, I got to come up with an algorithm, a formula to figure out how many seats to overbook. I think here, I know at my old grad school, they sold 2.5 tickets for every parking spot they had. Right? Something very similar happens here, which makes sense. And why do they do that? Because not everybody shows up at the same time, and they want to sell enough tickets so everybody has a place to park, and people come at different times of the day. But they can analyze and see what's the probability there's a time of the day when there aren't enough parking spots. Have they done that? I have no idea. About 5 weeks in, normally it doesn't matter. There's plenty of spots, unfortunately, but that happens. So let's build this up with something very basic, something we can actually count, and then I'm going to talk about how to make the leap to when we can't count everything. Right? So let's say I have 5 people selected at random. And we know that the probability that somebody's left-handed is 11%. The probability that any person is left-handed is 11% chance. Okay. If I picked 8 people, would the probability that a person is left-handed change? No. That's just 11% chance somebody's left-handed. I don't care how many people you pick, that stays 11%. I like it. So what's probably somebody's not left-handed? 89%. All right. Cool. I like it. I like it. So if I pick 5 people at random, what's the probability that exactly one of them is left-handed? So 5 people are selected. We know this. So it's probably that exactly 1 out of the 5 people, and I'll have people do 1 divided by 5, which doesn't make any sense. Where'd the 11% go? It's got to have something. Okay, good. I like it. So, if I said the first person is left-handed, that would be 0.11. But this is exactly 1 is left-handed. So who could be left-handed?
Anyone.
The first one could be left-handed.
Yeah.
And let me call not left-handed, well, let's see, we'll just call it N. Because not left-handed doesn't mean you're right-handed. You could be ambidextrous, or you could be equally horrible with either hand, right? Or you could have lost both of your limbs, I don't know, in a horrible threshing accident, I don't know, so you gotta be careful. So you're left-handed or you're not. So it could, let me see, does everybody understand what it means when I say that? What does that represent? The first person is left-handed, the other 4 are not. Or, what's another way that exactly 1 could be left-handed?
1 minus 1.
No, come on. The first one could be left-handed, or the second one could be left-handed, or the third one could be left-handed, or the last one could be left. Oh, my ends get really free. Shit. So can you see that this list very quickly gets stupid big? This is related to something that really seems weird to you guys. If there's like 14 toppings for a pizza and I can choose whatever, how many pizzas can you make? It's like 7 million or something. It's been a while since I did the calculations. 7 million different types of pizza you could create. And then if you bring in, well, you put half on, oh shit, now it's like insane numbers. Half pepperoni, half pineapple. Oh my God. How are we doing? Have you guys ever heard of that? Yes. I mean, when I ask people how many pizzas you have, like 1,000? No, 7 million. Holy shit. So if I had 10 people and I picked 2 of them that's going to be a pretty damn long list. It could be the first two, or the last two, or the middle two, the first one, the third one, the second one, and the eighth one. And holy shit, I don't want to make that list. Right? So I'm not going to make you do that. I'm just doing that for the first one here to get the idea. Then we're going to let the calculator count how big the list will be. Okay, so for this first one, we're going to do it by hand because it's small. We can handle this shit. Let me call. Tell me how many possible outcomes is there for each person?
One. It can be right or
How many? So two. There's two possible outcomes for each person. They have to be left-handed or not left-handed. So that's why we call this binomial. Two categories, right? So this is a binomial probability question. Two possible outcomes. There's going to be a probability of success and a probability of failure. Success doesn't have to be a happy thing. Success could be finding a dead body if that's what you're looking for, right? It's around here somewhere, Justin. I know he's dead. I'm going to look for this dead body. Or a rabbit, squirrel. It doesn't have to be nice. It just has to match what you're looking for. So what's the probability of success for me? What am I looking for? Left-handed, right? So I'm going to call the probability of success. I'm going to give that the letter P. And the probability of failure, I'm going to give that the letter Q. Cool, I like it. Notice also, if I pick these 5 people randomly from America, whatever, or from the earth, does this guy being left-handed affect the chances that the next one is left-handed? That would be really strange, wouldn't it? Line up, whoa, I'm left-handed now. No, sorry. So these are independent, which is why I can continue to use the letter P every time. It doesn't change. So I can just give it one variable, P. So how would this look if I use those instead? P, Q, P, Q, blah, 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 right? All right, now, let's use some algebra to make this better. Why am I multiplying each of these? Because this is the first guy is left-handed, and the next guy is left-handed. Now what? Or I could have the second guy. Or so I'm going to add these, right? So this is all multiplication. This is all adding. So what does each of these look like algebraically? Algebra would go, that's cute. You're floating the P through there, right? But what does this look like? P times Q to the fourth. I like it. All of these things look like this. Now, how does that relate to the question, actually? 1 success, right? There's a 1 here, right? 4 failures. Let me make that 4 closer. It's just freaking me out a little bit. There we go. Now, how many of those do I have in the list? 5. So what would the exponents have been if this would have been 2 successes, 3 failures? There would have been a 2 here and a 3 here. Stay with me. I'm starting to show you how setting this formula up is going to be really easy. This is going to be the part that could be really hard if I made you figure it out yourself every time. That's the part we're going to ask the calculator to do for us.
So where did you get the 5?
Where did I get the 5?
Yeah.
I have 5 ways to get PQ to the 4th. So what's PQ to the 4th plus PQ to the 4th plus PQ to the 4th? 5 PQ to the 4th. So what number is always going to go here? How long the list is. I like it. So if it was 10 people and I wanted 2 left-handers, that list would be rather large. Larger than you would probably consider. We're going to have the calculator tell us how long the list would be. All right, so let's actually do this. Well, this would be 5 times, what's P?
11.
0.11, there it is. Times 0.89 to the 4th. Try to put that in the calculator and see if we all get the same answer. In case you don't know, there's your to the button right there. To the fourth power. So that's true. If the probably left-handed person is 11%, there's almost a 35% chance there's one left-hander out of any group of 5 people. How many people in here are left-handed? Anybody? I'm not. 1, 2, 3, 4, 5. Wow, it's pretty good. Here comes the exciting part. 2, 4, 6, 8, 10, 16, 18, 20, 22, 24, 26, 28, 30, 32, 34, 36, 30. 40, 42, 43. All right, so 5 out of 43. What's 5 out of 43? That's neat. This is barely over 11%. It's like 12%. Is it? What is it? All right, now it didn't have to be like that because are you a random group of people? No, you're not. You're all here at this time taking this course. You have things that tie you together. But I still would expect it to be around 11% with a group this size. Because that's what's true for everybody. So it should be that way for any group of random people. So it could have been off, but hey, you guys right there. I love it. Okay. So what the hell? How do I do any general problem? So here's how we're going to do this. Let's take a look at this formula.
I think there was one of this kind of problem in the chapter 3 homework.
Nope. They're very careful. They're always saying, they don't say exactly one, they say the first one
Dice.
and the last several. They never say just probably whatever. Now I can't remember if there could have been one.
There was a problem with 2 dice.
Oh no, then you had to create the sample space.
Yes.
So you had to actually create.
Not only the sample space, it was like one is 3 or the first one would be 3 or 4.
Exactly.
The second would be,
Yes.
And then after that there was another one.
All right. That's not this kind of problem though. Thankfully, that would be really evil. For that problem, you had to make the sample space. If you roll 2 dice, what could happen? You get 1, 1, 1, 2, 1, 3, 2, 1, 2.
Yeah, but there. Okay.
And then you can just count. Once you set up the sample space, is this more likely than this? Is this, if you roll 2 die, getting a 2 and a 1, is it more likely than getting a 1 and a 3? Is one more likely than the other? They're all equally likely. So once you create the sample space for the problem, you just count what matches. That's it. I like it. Okay. So look at that formula there. It looks like the formula for the probability. Let me set up a few more variables here. X is going to be the number of successes, which makes sense because that's what can vary in the problems, right? Let's probably get 3 people that do this. We'll probably get 8 dogs that like this kind of food. That's the variable, the number of successes I'm looking for. So I'm going to call X the number of successes. N, thankfully, is just the total number of things I got, as always. Very often we call these trials. But if I got 5 people, then N is 5. That's awesome. N is one of the few letters that just stays the same meaning throughout. And then I got P and Q. What's true about P plus Q? Always. 1, because they're opposites of each other. All right. How are we doing so far? Everybody was decent with this, right? Creating this. So where did everything come from in this? So if I want X successes and there are N total things, what am I going to have? So the probability of X. Where did this come from? Length of list. Is that cool? That's how many of them I had, because I'm adding each one. So of course it's just going to end up being how long the list is. Times P to the, why is this P to the first? Because what was the question? The probability I get exactly 1 success. So what's the exponent in general? No. The probability to get X successes, so how many P's am I going to have? What does P represent? The probability of success. So if I want X successes, how many P's am I going to have?
P of X.
X. Just wait till we get to a problem, because it really kind of sets itself up. You have to believe me. Again, like I said earlier, why did I say that? If I said exactly 2 people, this would have been 2, this would have been 3. So the number of successes is how many P's I'm going to have, because P is the success. And so now here's the one that's a little bit freaky in general. What the shit is Q's power going to be?
No.
N minus X?
N minus X. If I had 8 people and I want 3 successes, how many failures? 8 people, I want 3 successes, how many failures? 5. 8 minus 3. N minus X. That's how much is left to be failures. This is the part that we have to talk about how to do this on the calculator. So we're going to do that right now. I'll wake him up. And then we're going to do a problem, and I want you to see how it kind of flows in. So let's do that problem I keep talking about, that 10 things, choose 2 of them. So if I had 10 people instead, and I want 2 people to be left-handed. So from the 10 people, I want to choose 2 to be left-handed. I choose 2 of them to be left-handed. I don't choose and make them left-handed. I mean, that's my choice for the situation I want to count. Right? So watch how this sets up. You gotta love this shit. You ready? What letter do you hope would be used in something that's supposed to be choose? You'd hope there would be a C in it. Yeah? So here we are. 10, put 10 in there. 10 people. Oh, let me zoom out a little bit. Shit, that's brightness, Jeff. There we go. Oh, there's buttons on this thing. 10. Now hit math. We don't use that very much, do we?
Yeah.
Which one of those do you think we're going to use? Under math. Everybody under math, hit math? You guys see all this? Which one of those seems to relate to what we're doing?
Number.
No.
Oh,
Probability. So if you got a probability, which one of those matches what I promised? Not National Public Radio. Which one has a C in it?
3.
So NCR means N is 10. They use an R instead of an X. Just forgive it. Right? Poor little calculator. So 10, choose 2. If you have an older calculator, it won't look like that, but enter. So that list, how many ways is there to choose 2 people out of 10? 45 ways. That's bigger than you probably really considered. It's not in the millions, but hell, that's still way bigger than you probably thought. There's 45 ways to choose 2 people out of 10. I like it. So, yeah, so I'll do it again. So 10, math, probability, choose. 10, choose 2. Alright. So let's try a real problem out from the beginning. That's good, Jeff. Well, I did work. Right. So if I know the probability someone likes broccoli is 39%. I pick 14 people.
You want to move the...
Oh, thank you. You guys in the front row, you are my assistants. You get paid nothing. It's an internship. Pick 14 people at random. What's the probability that exactly, what you got, Jeff? Exactly 5 of them like broccoli. Now, I really want you to understand, so far we're doing really stupid problems, right? We are. You know, like, who gives a shit? Just asking. We're getting to know how this formula works, and this is the formula I would use to do such things as figure out how we can make money in this airline. How many seats do we oversell? Right? I mean, you can see how this might lead to that. We'll get there. So the formula now, let me generalize this formula a little bit better now. In general, the probability of x is n choose x, p to the x, q to the n minus x. We knew that. If this many people choose this many to be successes, so then I have that many successes and the rest are failures. You can actually read that shit. So an equation is a math sentence. You really should be able to read it in English. It's just a translation problem. So what do I know from the problem? You always want to do this for yourself. What's n? What's p? What's q? What's x? What's n? 14. Total number of people, 14. What's p?
5.
No, 39.
0.39. What are p and q? What are they physically? They are probabilities. Together they make 1 because they are opposite probabilities. So the probability of success, what's a success? Liking broccoli is a success. So that's 0.39. What's q? The rest, 0.61. Do this in the calculator, because a lot of you guys are just going to say 0.71, which is really silly. That's more than 30, so that has to be less than 70 to make 1 total. Don't let your brain just go, I got this, and shut up, brain. Because you do this shit wrong, everything's wrong after that.
And how do you get this 61?
If 39% like broccoli, how many don't? The rest. Yeah. So that's why P plus Q is always what? That's a quick check. Sweet. I love it. And then what's X in this problem? 5. That's 5. Successes is X. That's what can vary. Couldn't have asked 4 successes. I could have asked 3. That's why that's X. That's the variable. So how does this get set up? Let's see. Probability of 5 equals, what goes here? Now it's just a chip plug and chug. 14. Choose. How many successes?
5.
5. So how many of these 0.39s will I have? How many of those will I have?
1.
What does 0.3? What does P represent? The probability of success. How many successes? So how many 0.39s will I have? 5. So how many are left over for the 0.61? 14 people. 5 of them that first one. How many are left over? 9. See how the formula, and it's not the formula's fault. Formula makes it look difficult. When really this is just who's left. 5 are there must be 9 there because there's freaking 14 people. And we're not letting any of them leave. You are in this room, eat the broccoli. No. So see if you can plug that in the calculator. Be careful if you have the newer one. Well, let's see, no, I don't think that, let me see if it does this to you. Workday jobs. Yeah, you do have to hit the over arrow to get back up. Because you're down underneath the seat. You gotta hit the over arrow to get back up. Then keep going. Times. That's what it looks like there. People at home. So we get 0.2112. Schwab. All right. I love the expression on some faces, but I'm not hearing any questions. So let me give you this. You know me. I get a handout. So just, I want you to work on this hand now. You can work together if you want to. Don't like other people, you don't have to.